Ed,
Hey,
what's up?
I'm looking at a calendar and I just realized I booked a flight for the wrong day again. Oh my goodness.
I've booked quite a few flights in the last 3 days.
I got to be able to sit in a quiet room and do this stuff because I was talking to somebody sitting next to me and booking stuff, and I don't know why I decided to just look at it now, and it's saying Sunday, and I'm supposed to leave Saturday, so that's going to be a
Do you
well
sit, do you
something I'm going to fix, but
do you sit there and play the game where you shop different airlines and try to say like Delta? Like when I was shopping for the airlines the other night, and I'm like Delta, Southwest, because I have like cards with them, so I'm trying to like optimize my best moves here. But then like Delta's always like $800. I'm like, well,
yeah,
that's not what happened this time,
I
Delta.
play the game. Well, I used to play the game. We have a thing now that we're supposed to use, and it's just use that. And I'm not going to say it doesn't matter what it costs, but you go on the service, and then they show you like I don't know half a dozen different airlines. And if I'm flying and it's coming out of my pocket, I'm looking at Spirit and I'm looking at Frontier, and I'm like, oh man. And I hover over them, and it doesn't actually say this, but in my mind it says, no way, no way. And then it won't let
Yeah,
me
yeah.
book those airlines. And I was like, all right, I like this a lot now. And it's
Well,
it's
when I
almost weird. Like I'm booking for Vegas. You're going to Vegas for the
yeah,
ESCO thing, not that in a couple weeks. And I was having a difficult time, and I still didn't get one. I'm going through Chicago again. I can't get a direct flight, but I can get a Spirit flight direct. And I'm like, I'll sit and I got short legs and my feet dangle in an airplane seat. So Spirit doesn't bother me as far as being compact and all that.
okay. Have you ever noticed that maybe if somebody's in the chat and they fly a lot? I haven't flown Spirit or Frontier a lot, but isn't by the time you get all the fees, it's like the same price?
No, no, the $9 club, they charge you $38 for the government fees each way. But my kid lives in Florida. We have an airport that's like going to Home Depot. It's like a half
Oh
hour
yeah,
from my house. So we fly Spirit a lot. And yeah, they nickel and
I need
dime
to
you
check
to
into
death.
that.
But uh, two of us, if we don't take a bag, we get there and back for $150 for
Oh
both of us, not a piece. So
wow,
yeah,
yeah,
it's cheap.
that's really
So
cheap.
it's only a 2 hour flight, and it's not that bad. And
Hmm.
get
All
liquored up
right.
before you get on the plane. It works out pretty well in the car. Oh.
No rental cars happening. Huh? Nothing but
No, the kid comes and picks me up, or her boyfriend picks us up. And heck, man, the rental cars. The kids in Florida down there by Disney, man, it's like going on another ride. You get in the rental car and jumping curbs and doing. Not that I would ever do that. Neutral dumps
no,
and
not that we would wreck any cars in Orlando, right?
you got to turn that traction control thing off if you want to do good burnouts
Did
with
you
it.
see
I
my
think that's
post about from the van we rented and someone drew like the sign, the cross sign? Did I tell
I
you this
got a
story
ride
about
back
that?
to the airport with Alex Meany, and somebody drew the same thing on his windshield. I
Okay.
think it was the kids that rolled the golf cart trying to
Well,
retaliate for us, yeah,
well,
yelling at them.
I didn't know this, but there was like a nice dent in the back of the van. And so when we went to turn it in, I was joking with the guy about I said, well, we had to have a target, because we were drunk trying to get home. And he laughed. And then he goes, what about that dent in the back? And I thought he was messing with me. And I was like, what dent in the back? And then Mike Barnes is back there taking pictures of the dent. And I'm like, oh, man. I was like, that plus sign doesn't look really good right now. But speaking of HVAC excellence, let's talk about the weekend, Ed. This was my weekend. All right, here we go. Bam. What do you think about that right there? That's slick.
that
That's a
that
piece.
gives you the
That's a work of
ability
art.
to check. I can't think of anything on that you can't demonstrate. And
That's a 3-day build, man, for me right there. So that is a wooden. I was shopping for a cart, a metal cart, and I actually ordered a cart for like $1,000 from Fastenal. And then they called me and say, hey, that cart's discontinued. You can't get it anymore. And I was like, are you serious? So then I went to their distributor, which is like Jamco or something like that. And I called them. I said, hey, can I get the cart from you? And they're like, no, it's discontinued. I wanted a cart that would roll through any doorway because my plan was to put it here and train on it right here.
What, 36? You're trying to stay 36 inches and under?
Under 32 inches.
Oh, really?
Yeah. So I was like, and I knew a 1.5 ton condenser would fit through a doorway. So I was like, you know what? I'm going to build this and I'm going to make it to where it can go through any 32-inch door. So I built it and it took me about 3 days. It's got double returns and a filter slot next to one of the returns. So I can do true flow, multiple true flow, you know, that whole scenario shebang.
I picked up on that one.
And I had an Ecobee laying around. So I threw an Ecobee on it because it was free to me. Actually, I had 2 of them laying around, and Adam's brother got the other one the other day. So I'm out of Ecobees for free. If anybody wants one, you gotta buy it now. But anyway, so then I called the company and I said, hey, it's on wheels. Can I ship it to Vegas like that? And they said, oh, no, it's got to be in a box.
Yeah.
And I was like, really? I'm like, even if I crate it up, it's got to be in the box. They're like, yeah, it's got to be in a box. So Saturday, I built a box.
Nice.
Yeah, let me tell you what, that's almost just as much work as building the air conditioning system. But I did build that ramp. So I made the door the ramp, which I thought was pretty cool.
No, that's definitely a good idea.
And then,
do you have something inside of it to like put some perforated strap around the duct and screw it so that when it's shimmying and shaking?
That's tomorrow's project. So I'm going back. That's my dad's house, right? That's his shop. And I'm going there tomorrow. We're going to load it up. And then I got to figure out how I'm going to like manipulate this machine in that box so it doesn't get beat to death on the ride.
Yeah.
So I'm going to go steal all my kids' pillows that are probably in really bad shape and stuff pillows all around this thing.
I would take like some cleat or whatever and screw it to the duct and screw it to stuff so that it's like one rigid mass instead of it being able to be all kinds of flexible inside there.
Yeah, I don't know. We'll see what happens.
Yeah,
man. We'll see what happens. But then, you know, I started thinking, is this necessary?
If you want to get a bunch of people standing around with their hands in their pockets, staring at the ground, acting uncomfortable because they don't want to talk, that's the way you get them to start talking. If they can put how many times have you heard people say I'm a hands-on learner? Because what they're really saying is, I don't want to read instructions. I want you to show me how to do it. Because that's me.
I started thinking maybe Steve's messing with me. So I have this like idea that Steve and Bill are in the background and they're just joking with me. Saying, you know, let's see what we can get him to do this week. So I like memes, man. I thought this fit the bill.
They did.
All right. So we got a guess. We're going to be talking airflow, static pressures today. I'm going to bring Russ King in, and then I got some videos to show on lab test data. Me and Ed. So let's go ahead and get Russ in here. What's up, Russ?
Hey guys, how's it going?
We were just talking about you behind your back.
Yeah, I heard every word of it. I'm saying I'm right here. I'm right here. Hey, I do have a confession though. So when we left the house in Florida, Connor and I had to catch a 7 a.m. flight that morning. So we were the first ones out. So I was the one who drew the missile sights on everybody's car. You're lucky. If it was someone I don't like, if it's somebody I don't like, I draw a crack, like their windshield's cracked. You know, well, you guys are lucky. I like having a missile sights on my car.
You should have been at the car rental return. You would have enjoyed that conversation. All right.
Funny.
So tonight's webinar, we're talking about airflow, of course, and we're going to talk about static pressure locations. And I've got some videos prepared, and I want to play one of them right now. Hold on, let me dig it up. Let's see. All right. I'm going to play the first one of me and Ed doing some static pressure testing across the evaporator coil. Ready?
I'm recording you right now.
That's fine. Well, you can cut it. Again, I don't care.
I hate that guy, man. Look at that.
See, I like those numbers right there because they're driving home the point that I'm trying to drive home right now.
Yeah. Drive it.
And
dude.
it's recording?
Drive it, yeah.
Okay. Have you ever been curious if the location of your supply static tip downstream on an evaporator coil when measuring pressure drop across an evaporator coil matters? Well, you don't have to be curious anymore. What we have set up here is our static tips in the supply downstream of the coil, and then via these T's, we have one reference point or one static pressure measurement on the return. And as you can see with these gauges, we're seeing less than 3/100ths of an inch discrepancy between the three gauges. So the conclusion?
And that's on 10-second averaging.
10-second averaging, so it gives us an even better reference point. The conclusion, it doesn't really matter if you're left of center, in the center, or right of center.
Take it away, Ed.
I was on a quest to take that measurement. I want to, I don't know if I'm correct when I say this, but when I first got there, I was talking about the first test I wanted to do was where the
Yeah, you were really adamant about that one.
yeah, and without getting into a long story, somebody disagreed with me once, and I was like, well, I don't have any proof until now that it doesn't make any difference where it is. The idea, well, static pressure, right? Static and pressure. I use a picture of a balloon to demonstrate static pressure. And I would think it doesn't matter, but when somebody's adamant about it does matter, well, one of the things I do want to mention while we're talking about this, as much as I would like to have 500 samples of this stuff, I think even with the anecdotal evidence that we have with one test, it's going to come up the same way every time. There are some other things we might do that we might get some stuff jumping around and some different numbers at times. But with this one, I think this one is going to be exactly the same every time. So even though it still is anecdotal, I'm going to say it's a pretty solid test for what we were trying to determine, and we determined it.
Yeah. I got one more video I want to show, and then I want to switch gears. I want to show the video, talk about it for a minute. Then I want to switch gears, and I want to go to like design side of things with Russ. All right. So this is another static pressure video where we kind of ruled out the myth of, well, in general, where to place your static pressure probe, right, when taking external static pressure. So here we go. So Ed's here. He just got in right off the airplane, and we're about to do some testing.
Boy, are my arms tired. I had to say it because I had to. One of the things that I've always questioned when it came to do with airflow measurements, especially static pressure measurements, was how accurate are they and how important is the actual location where they're taken? Well, I don't have to wonder anymore. I got my answer today.
So we're going to take you through a test on this system behind us right now. Okay, here's what we're going to do. Ed wants to see what's the most valuable and accurate measurement. So we have a furnace here. We have a coil right on top, no transition. We have drilled 5 holes right at the top of the furnace. We're going to apply a static pressure probe in each one of these holes, monitored by the 3 gauges we have above. 2 DG1000s, so we have dual channels, and we have a single channel on the DG8. We're going to see how this turns out. All right, if we check static after the filter before the blower, we have a low of 0.19 and a high of 0.19. It's basically the same. Now, if we go to the other side of the furnace, but on the return side, we have a 0.26 on the high and a 0.25 on the low. Now, if we go to the supply side, but before the coil, we have a high of 0.18 and a low of 0.14. Now, that basically means we either have a external static pressure of 0.34 or 0.44 between the measurements. Take that to the blower chart, we either have 865 CFM or 903 CFM. We're in between that margin. We measured it with the true flow. We have 837 CFM of flow at 0.35 external static pressure. basically meaning our blower chart could have a margin of error of 4 to 8%. Busted.
Yeah, I was disappointed when we saw the accuracy being that good. I wanted to be able to badmouth external static pressure on a new system for the next 10 years. And based off of that, I can't. I'm saying that the fan tables are accurate. I mean, in some respects, I can't say I was really surprised because I expected them to be accurate, but I was cheering for the underdog. And the underdog was it being wrong, and we walk around all snooty and saying, "Don't do that. It's not a good test." And once the stuff gets dirty, it's not a good test. But I wanted to be able to poo-poo it just for the sake of being able to poo-poo it.
So studying that test, taking the measurements right after the filter before the blower where it was located seemed to be combining that with before the coil, after the furnace. Those two measurements were the closest and the lowest measurements to get us close to what the true flow measured. When we measured static on the bottom left of that air handler, the static was actually higher. No, I'm sorry. Higher static would be less flow.
Yes.
So actually the better measurements would be on the bottom left side of the furnace than right after the filter, because it's actually showing a lower static, which is incorrect to what we measured. So if you're out there and you're listening, you should be checking static at the bottom left of the furnace rather than right after the filter.
Well, that goes back to the dead areas, right? Where there's less flow, less turbulence. So
yeah,
I'm going to say that makes sense. That one's not a surprise.
I was always told to take several measurements and use the lowest measurement, because if there's any place that has a higher measurement, it's probably because you're catching some of the velocity pressure.
But generally,
I would agree with that.
We're at 4 to 8%, So ideally, if the system's clean, it's, in that orientation, we're not that far off, So it's not a bad method to use to estimate airflow.
Oh, and there's the key word.
That's right.
That's not measuring airflow.
I snuck that in there just perfectly. As estimating airflow, and then there's measuring airflow, right? There's a difference.
Absolutely.
That's what they pay me to say.
I think the static pressure, one of the best uses of a static pressure test is for evaluating the size of your ducts. And did they do a good job sizing ducts and everything? Because you get in there and measure 0.8, 0.9 static pressure, then they didn't do a good job. So,
yeah. So I'm gonna answer a chat question or two before we jump into your data. But HVAC overtime, I think that's Adam. He said, did we try to spin the tip to see if we were picking up velocity pressure? I really didn't have any room to. Like where the tip was going in, like when I got it in, I barely got it in there. So I didn't have any really room to kind of spin it around. I guess I could have above the furnace, below the coil. But that's the only one I guess I didn't rotate. The other ones, it was hard enough getting it in there.
Well, Chris, do you remember laying on the floor taking a picture inside the duct while we stuck the static tip in and spun it 360 degrees to see if we saw it?
Oh, yeah. Oh, you talking about when we were doing the compression testing?
Yeah.
We were rotating the tip. Yeah.
Yeah, and I didn't realize that we were sucking on the duct. They were blowing on the duct. And I was giving the data to Steve, and he's like, well, that isn't making any sense. And then we realized, I realized that the air was going in the other direction. I mean, static pressure doesn't care as far as the direction of flow. But it was one of the things that I was interested in testing was how much of a difference does it make when you spin the tip? And Steve has the data and never shared it.
Yeah.
I'm joking, but I don't think I ever asked him for it. I think when that first night printed everything out. I don't, and if he wants to type in the chat, if he recalls,
I don't know if he's
interested. There was a discrepancy, but it wasn't nearly the discrepancy that I thought it was going to be. It was very small. I want to say it changed the measurement by percentage wise, it was a single digit. And there was only a couple of very specific angles you got on, and it wasn't 90 degrees to the flow, if I recall correctly. It was like 4 and 8 o'clock or something was when it was 7 or 8%. And I'm making those numbers up because I don't recall correctly. But it wasn't the seeing half or double that I wouldn't have been surprised if I saw. But I've spun the static tip in a lot of ducks over the years to see if I could get a big difference. And there is the rare occasion, back in the day, you'd see the needle on the MagnaHelix going back and forth like this, but they were few and far between. So testing it in the lab, or on the floor of the warehouse, depending on what you want to call it, but in the lab, we really couldn't get it to be a big discrepancy.
Kind of reminds me of the whole basketball needle conversation.
Yeah.
All right, let's get into Russ King's data. So now we're going to switch gears, right? We've kind of established that where taking static comes into play. We tried to bust the theory. We tried to get like out the box bad example of static pressure measurements on a clean system, and truthfully, we couldn't get crazy off. So system's clean, you're probably within 8%. Unless you get another orientation that's really weird. I'd love to see some data if anybody pulls that out and can prove us wrong from there. But so far, we're standing the ground to say we're hitting about 8% of inaccuracy. All right, so switching gears. Russ, this is your content, man. So you're here to talk about airflow and airflow design. Sure. Tell us what we don't know.
You got it. I think, when you're teaching manual D, I think one of the hardest concepts to get across to people is that you're teaching them how to design a duct system so that when they turn it on and measure that static pressure, they're going to get a number they expect. How do you design a duct system to get a certain static pressure? And the way you get that is you use it in your design calculations, right? And that number gets plugged into the friction rate. And the friction rate is what is used to size the ducts. And if you follow that process, you can predict what that static pressure is going to be before you even turn the system on. And I think that's a really hard thing for people to grasp, but it works. I've seen it worked on literally hundreds and hundreds and hundreds of homes that we've tested, and they came in always just slightly below the number we designed to. And we pretty standard practice was to design to 0.6. And we would always come in right around 0.54 is right about where we would come in and get a real good airflow. And out here in a dry climate, we want as much CFM per ton as we can get. However, we were designing to a lot of tract homes, and builders were pretty cheap. They didn't like to go super cutting edge or anything. So we were designing pretty standard, what I would call a C grade house. So I think, just learn manual D and get used to it. And what I always tell people in classes that I teach is you don't know anything until you've actually gone out and tested a house that you've designed. That's that amazing feedback that you get. That's where the light bulb goes off. And I was really, really fortunate in some of the jobs that I had is that not only were we doing designs, but we had a whole team of field people called HERS raters that would go out and test these houses and actually write the actual CFMs on our plans and send them back to me. And I could look at them. And when we first started doing it, I was, there were a lot of ducts were off quite a bit. The total airflow was good, but a few of the ducts here and there were off at the supply register. But after a while, we got to where we were nailing it. We were within 10%, always slightly over, but it was good stuff. So basically, this is just a little sample drawing that I use all the time. 99% of the systems I've designed were horizontal units in an attic. And so that's basically what you're looking at here. And one of the things that a lot of people also don't understand about designing systems like this is you can't just look at one run. You can't say, oh, this is a bedroom. I think it needs about this much air. What you really have to do is think of that bedroom as a percent of the total airflow. You have to look at the entire system. You can't, because you might have a small house that has 800 CFM going to it, and you might have the exact same size house somewhere else with 1200 CFM going to it. Well, it's the exact same size house, and it's the exact same size rooms, but because of where it's located or the orientation, it's all about percentages. So in order for one room to be comfortable, it has to be within its percentage of the total. And so, we kind of hammer that in a lot of the classes that I teach. So
share the air.
Share the air. I call it the fair share of the air. Yep.
Yeah, I sometimes give you credit for that when I repeat it. If once in a while I'll say, yeah, I learned this from Russ King. And sometimes I just say it, but it's a good way to describe it because it's accurate.
Yep. Fair share of the air.
Russ, there's a good question in the chat I want to bring up. Okay. What is your opinion on sizing trunks using manual D, but also targeting balanced velocities in the trunks?
Honestly, I rarely care about velocity. I can't think of a time where I've actually changed the duct size because of velocity. If you follow manual D and you're within, their range of friction rates of minimum 0.06, maximum 0.16 or something like that. I'm drawing a blank on it, but if you're in that range, your velocities are always going to be within a certain range anyways. And, the vast majority of the systems I designed were flex duct. Velocity caused noise in flex duct is almost non-existent. So I honestly, I'm far more concerned about airflow and getting the CFM through that duct than I am about velocity and making sure that the flow is good. And if you worry about the friction rate, that almost always works out fine.
Okay. I'm going to switch gears a little bit and show this picture.
Yeah, so I used to have to work with a lot of new construction architects, and they had no clue about airflow. And, so I would say I would draw on the plans that I need a 12 by 12 clear chase to get a 10-inch duct down through. I didn't tell them that because then they would make a 10 by 10 chase, but I wanted to leave room for insulation, all that. And then I get out and then I get a call from the field going, yeah, you drew a 12-inch duct, but there's no room for it. I go, what is it? And they told me, and I called the architect. I told you I needed a 12 by 12. He goes, well, instead of a 12-inch duct, I gave you 2 6-inch ducts. That should be good enough, right? And so I'm just like, oh man. So this is just an illustration showing that 2 6-inch ducts are not even close to a 12-inch duct, And I think I use the analogy of trying to trade 2 6-inch pizzas for a 12-inch pizza, or something like that. But so this just shows all that shaded area is what you don't get from the 2 6-inch ducts that you do get from the 12-inch. So you can see there's a huge difference, and there's a lot more to it than just a cross-sectional area too. I think if you go to the next slide, I think I'm not sure which slides you have, but
I'm not sure if I have that slide or not. This is what I got next.
Oh, okay. So basically what the architect was saying is you can't get one big duct, but I've given you enough room for 2 small ducts to get down. And so let's say I was getting a 12-inch duct, and so I needed 500 CFM I needed to get 500 CFM to the first floor of this house. And so how many 2-inch ducts and what size would they be in order to get the same CFM? And so based on this chart, which I'll explain in just a second, to get 500 CFM, even 2 9-inch ducts isn't enough. That would be 460. So I would need a 9-inch and a 10-inch duct. So in order to get a rectangular chase that has 2 ducts in it instead of 1 square chase, I would need a 10 by 19 chase to get the same size ducts down and get the same airflow. And so that's just kind of what that whole illustration was about. But what this is, and this is funny, this pops up all the time.
This came up in the chat one day, and I don't know. I feel like it comes up a lot. So that should be good because your data is getting around.
Yeah.
But I feel like this one gets misused or misunderstood. So I wanted to bring it up so you could put it out there. You know what I mean?
Yep. And all I did with this is I took the ACCA, the big ACCA wheel, which I've got right here somewhere. I can't reach it. The ACCA ductulator wheel. And I just went to a friction rate of 0.1. There it is. And the nice thing about the ACCA wheels is that it's very precise. It's a lot easier to read smaller numbers on it. And it has 3 different types of duct. So it has flex duct, metal duct, and duct board on it, which is really cool. You don't see that very often. But all I did is I went to a 0.1 inch friction rate. Okay, it's 0.1 inch water column per 100 feet. And I just said, okay, how much will a 4-inch duct give me? And it was about 20 CFM. How much will a 5-inch duct give me? It was about 50 CFM. And I just went right down all the duct sizes, and I wrote down the airflow for each one. And I rounded it to the nearest 5 or 10 or whatever, rounded up just a little bit. So, and I have a collection. I want to say I have 7 different ductulators, and 5 of those are for flex duct, and they will all give you a slightly different number, okay, than from each other. So even the ductulators will vary somewhat. So keep that in mind. Also, there's different types of flex duct. Cowflex versus some of the other ones versus another manufacturer will publish a what's it called, Ed? The friction factor. It's the.
I was paying attention, and I don't know what number you're going for.
It's the for like metal is 1.0, and then most flex duct is like 1.7, and then duct board is like 1 point something else. It's a number that describes relative to sheet metal what's the resistance of airflow.
Oh, okay.
That duct. And
then it
like
a roughness factor.
Roughness factor. That's it.
A drag coefficient.
No, roughness factor was the number I was looking for. Yeah. And even different flex duct manufacturers will say they have a different roughness factor for their ducts. So the point is that they're all going to vary a little bit, but the difference between sheet metal and flex duct is pretty substantial in terms of airflow that a certain size duct will give you. Okay. But the important thing to understand about this table is that it is at a friction rate of 0.1. Okay. 0.1 inches of water column per 100 feet. And basically, you think of that as your burn rate, okay? For every 100 feet that you go down this duct, you're going to burn 0.1 inches of static pressure. And so you're starting with a certain static pressure, and you're going to burn that as you travel through the ducts. Well, that burn rate is a function of the way the ducts are laid out. How long is that duct? How many fittings are in that duct? And all that other kind of stuff. So what I really try to emphasize to people, even though I'm guilty of it, I use 0.1 inch all the time because it just seems to be a number out there. And I think the disservice I'm doing by using that number is that I'm making people think that that's the number they should always use. But I always try to tell people, you have to calculate the friction rate for whatever duct system you're designing. You can't just guess. You have to calculate it. And like I said before, Manual D gives you a range. There's on there, you look at their friction rate calculator sheet, there's a range and there's a little graph, and the lowest they want you to go is 0.06 and the highest is 0.16, I think. But what's right in the middle of those two numbers? Right dead center is 0.1. And, I always, when we did designs, I always, kept kind of mental note of where we were, and we were always right around 0.1. We were, going downstairs, we might be 0.07, going upstairs on a attic mounted furnace, we might be 0.12, but we were always right around 0.1. So I use it all the time, but I can't emphasize enough that you have to calculate that number for that. So for a different friction rate, those airflow numbers will change, and it's totally counterintuitive. For a higher friction rate, a higher friction rate will result in smaller ducts. It's just weird. Okay. Chris, do you have the other one that shows multiple friction rates?
I do, but I just had to kind of make a joke because you were talking about friction rate and calling it the burn rate.
Yeah.
All I could think about is you live in California and everything's on fire all the time.
Yeah, that's true. Yeah.
And it's funny because my dad used to call it drag. And I was trying to think, what is he relating that to in Louisiana? I don't know. But anyway.
Yeah. So what this is, it's essentially the same information, but instead of having one friction rate, it shows 4 friction rates at different columns. So you got 0.11, 0.10, there's the infamous 0.1, 0.09, and 0.08. And what it does is it shows each color-coded section is a duct size. So the very first one is 4 inches, that pink section there. And so if you look at 0.11, a higher friction rate of 4-inch duct will give you a little bit more airflow. See that pink line, that pink color drops down to a little bit higher airflow. And as the friction rate gets lower and lower, the amount of air that a 4-inch duct delivers gets less and less. And it's very evident if you look at like an 18-inch duct on the right-hand side, the darker green color there. You'll see that there's, from a 0.11 to a 0.08, the range of air that you get out of an 18-inch duct changes quite a bit. So there's bigger steps between those columns. But what's interesting to me is if you look at those 4 columns with the green bars in it, there's a middle range where all the way across, there's a range of airflows, and I can't read it. Is there any way you can zoom in on that, Chris?
I don't think so, Russ. I wish I could. I tried to blow it up as big as I could.
So if you look at the far left-hand column, where the yellow turns to green, whatever that airflow is, maybe
See if I can. No, it won't let me.
Okay, but then if you go down to the far right column where the green turns to blue, whatever that airflow is, between those 2 airflows, it doesn't matter what your friction rate is. It'll still be an 18-inch duct. So you see that? So no matter what column you're in that center of that green shape there, whether it's 0.11 or 0.08, it'll all result in an 18-inch duct. So,
all right, so I'm going to bring up a debate question. So there's been a little bit of chatter about this kind of going around about why don't we just upsize our flex solid one size, right?
Yep.
I'd like to see this go into a battle, right? Is that a good approach? Should we, here's what I'm saying. You may say, well, if you design, that's the design, but nothing gets installed quite like it's designed, right? It's really hard to send a crew out there and they put it into perfection. So do we upsize flex? Is that a good approach?
It's an approach.
He's holding back something and he wants.
Yeah. So
when you say upsize, is upsize, people use the term oversize quite a bit when in reality they are saying properly sized. An example, if you have a furnace that has a 4-ton drive in it, but that 4-ton drive is going to be attached to a 3-ton air conditioning system, and it delivers the airflow that we want it to, is it oversized or is it properly sized? Right? That's not an oversized drive in my world. That's a properly sized drive. Same thing with the duct question. If you need to go up a size because you're going to exceed the 4% compression, and everything in manual D when it comes to flex has, and on the duct wheel, it's 4% or less compression. If you guys are doing some of this stuff, going up to the next size, is that really going up to the next size, or is that going up so it's the proper size? So all this comes back to what Russ started off in the very beginning with speaking about, was he was very fortunate where he did designs and then was getting feedback. And the industry is just loaded with people that know that 6-inch run is getting 190 CFM or whatever fantasy world they live in, and they know it because they used their handometer. They didn't measure it. And I'm a little bit guilty of that myself. The first time I ever put a flow hood on a duct in a house that we designed and we knew it was a good design, that $3,500 or whatever it is we spent was garbage, because that flow hood was a piece of crap and was only measuring half the air coming out of that duct. And it wasn't. It was measuring all of it. We didn't know what we were doing. We thought we knew what we were doing, but we didn't. So that feedback, anytime you talk to anybody that has had that feedback, it's a night and day difference, because the first time you put that flow hood on a 7-inch flex and it's only measured like 65 CFM, you get a bad feeling in your stomach, man. It's like, what else did I screw up in the last 6 months or 16 years? So it can be a big deal. All right, I'm looking at the chat, and I'll admit to my
I wanted it too.
I'm not real bright. I don't know how to sign in. I want to respond to these guys. So I just want to tell them I'm not ignoring anybody. My thing says log in. I can go in the super secret chat and it'll let me type stuff in. So I'm talking about all you guys as we're sitting here, but I can't converse with you in the chat. I can talk to you. All right, I'm done. I don't want to take up more Russ's time, but I had to get that one out.
Yeah, I think Chris, what you're asking is if you do your manual D and it's calling for a 6, you just arbitrarily go to the next size up just because, right? I'm
saying you draw your ducts, and let's say you're in a program, then your ducts, you cannot know how many turns you're going to have in that duct, right?
Right.
And the program's not going to necessarily know that. You get a house that gets framed up, there's all the blocking, right?
Yeah.
You got to go around it. So when they get out there, you can't blame the crews for rerouting the ductwork a little bit, but how does the designer take that into consideration? Do we just, and my idea is like, let's just upsize the flex. That way, no matter if they got to do some rerouting, we got balancing dampers. We can balance the job accordingly, but the guys don't have to worry about, oh my God, we made an extra turn. We just ruined the whole job.
Yeah. So what I would say for the designer is you can just arbitrarily add total equivalent lengths to your friction rate calculation. You can just say, all right, for every run, I'm going to add 100 feet of total equivalent lengths. And that'll change the friction rate, okay, which in some cases might change the duct size, but in a lot of cases it won't. When you just arbitrarily go up a duct size, it has a huge impact. So let's say your plan's called for a 6-inch duct, okay, and you go, let's upsize it to a 7-inch duct. And some people don't use odd size ducts, so they'd go up to an 8-inch duct, right? So a 6-inch duct will give you about 75 CFM. If you go up to a 7-inch duct, it goes up to 110 CFM. That's a 50% or a 33% increase in airflow just by going up. If you go to an 8-inch duct from a 6-inch, you've doubled the airflow. You've put a duct into the handle twice as much airflow. So I think that's way overkill personally. If you're worried about a few extra bends in the duct, what the designer should do is just imagine those bends are going to be there. Manual D quantifies a bend in flex duct. Just say every run's going to have 2 extra bends in it, and you can quantify that. Put that into your friction rate calculations and your total equivalent lengths. It'll change the friction rate, which in some cases it'll make the ducts bigger, in some cases it won't, because some cases it doesn't matter. The duct has enough excess capacity. And Ed clued me in the other day. I've always said for years and years that if manual D calls, if you put in 1 CFM more than what a duct will carry, it will round up to the next duct size. It's actually not quite that extreme. If manual D calls for a 7.2-inch duct, you can round down to a 7. But if it calls for a 7.3-inch duct, you have to round up to an 8. Even with that, there's still excess capacity. And that's why every time I measured a system that I designed, it always came in lower static pressure than what we designed to, because the ducts have that excess capacity. When you turn that system on, the duct's always a little bit bigger than what you need, except for the few that fall in the 7.2 range, and get round down. But overall, the vast majority of ducts are rounded up a size, and so you have excess capacity. So I just personally, I don't think arbitrarily upsizing is necessary. I think you can factor that into your calculations, your manual D calculations. So Yeah.
So I'm gonna jump off my high horse for a minute, man, and just wrap myself out. I used to lower my velocities on my designs,
Mm-hmm.
and I know that would upsize my ductwork. And I use that as my way to give my guys breathing room to make mistakes.
Sure. It's another way to do it. Yeah, it's another way to do it. But I think the most accurate way.
Yeah. No, I'm sorry. Go ahead.
The most accurate way is factor in what it is you're really worried about. You're worried about extra bends in the duct.
Yeah.
And bends can be quantified in terms of total equivalent length. So factor that into your design.
Yeah.
And if they don't happen, then that's fine. Yeah.
I like it. The conclusion in Manual D actually addresses that there's no such thing as having velocities that are too low. You can't have a duct. I mean, I guess you could have a duct that's too big if we're talking about stuff you could walk through. But there's a paragraph that is titled Conclusion in the back of Manual D, and it shows an example of using starting with a 6-inch duct and going all the way up, I think, to a 12-inch duct, and showing that you're moving, and I'm making these numbers up, like 120 CFM through it. And the idea is you're going to have obviously much lower velocities in the bigger duct, but at the end, your termination box and your grill selection is going to be the decider of your throw and the spread that you get, because 120 CFM going through a 10x4 grill, the grill doesn't matter if it was connected to a 6, 8, 10, or 12-inch duct. Yeah. You're going to get the same face velocity across the grill. So the one thing that I would always be careful of, especially in your market, Chris, I don't want the ducks that are living in that hostile environment to allow the air to move at a much slower rate than is desirable. I want that air to spend the least amount of time in that aggressive environment as possible. So that's an instance where I'd say Russ and I differ with the idea of, I look at velocity a lot, and if I'm in the unconditioned space, I want to run my velocity right up against the max. And if I have the ducts inside the conditioned space, I'm going to run them slightly at a lower speed. But I'm also looking at doing a lot more metal in comparison. And I definitely agree with what Russ says with the idea that Flex Duct produces a system that is quieter. So there's no arguments or disagreements there. I had mentioned to Russ when we were in Florida, I sat through one of his sessions, and it was the West Coast version of me, because the same stuff. And I guess this goes for anybody who has the full manual, the understanding of it, because it all comes back to the same thing. It's the same mathematical principles, and it's the same things that we keep repeating to try and get people to follow. Because if you don't make up stuff and you actually use math and visualize what it's going to look like, the sizes are self-evident when you go through the process. The friction rate worksheet it forces you to do everything that needs to be done.
Yeah. I want to point out something you said too, Ed, that a lot of people get wrong is they worry about the velocity in the ducts affecting the throw. And those are two very different things. You can have the air go really, really slow through the ducts, but it's the size of the register. It's the face velocity at the register is what affects throw in the room. So,
I have this tagline that I've been using for a long time. And when I just flat out tell people, if you got somebody telling you that they're doing something to keep the velocity up in the duct, they don't understand duct design. And if they want to give you advice on relationships, finances, or pregnancy, don't take advice from those people, because they're not the people you want to take advice from.
I got a question on that though. So I've sized some grills for a commercial job, and I remember studying this, and I remember, on the chart it says neck velocity, right? So they want to know neck velocity with grill size to get throw, but wouldn't neck velocity be considered like, is there some weird factor here that's we're kind of jumping over from duct to register, like right in the middle, like that neck velocity, the velocity right before it hits the grill?
You lost me when you said commercial, because that's
I just remember looking at these grill charts, and it could have been Hart and Cooley, but I'm not sure. But I just remember that it had a column for neck velocity.
yeah, and you'll see that. My understanding is when you're trying to pump a 6-inch round or an oval into a stack head, and the stack head's being placed in the ceiling, you have to account for, we have a 6-inch duct going through a 6-inch round oval, and then it's going to go into a 10x6 or a 10x12. So the size of the attachment point versus the size of the box has to be taken into consideration.
Yeah. So maybe there's something there. I don't know.
Yeah, and
January. All right, hold on. I got to switch gears. All right. This one's, I'm going to let Russ take it, but I want to make some comments on this. Go ahead, Russ.
Yeah, so this came about. We had a situation where a duct wouldn't fit past a beam in a house on the first floor. And so I told the contractor, I think we were calling for a 10-inch duct to go along. And I said, just neck it down to a sheet metal 8-inch duct and then go back to a 10-inch duct on the other side of this beam. And I didn't hear back from him. And then when we went out to the job site, he ran an 8-inch duct the whole way. And he goes, well, if you're going to neck down to an 8-inch duct, you might as well have the whole thing be an 8-inch duct because that's the smallest opening you have in the duct. And I went, all right, so here's how I explained it to him. So line A would be if it was a 10-inch duct all the way. And the slant of that line is equivalent to the friction rate. Okay, it's how much static pressure you're losing as you go across. So if it was a 10-inch duct all the way, you'd end up at point A. You'd have a lot of airflow. Okay, and at C, the smaller, the 8-inch duct, you would be on the slope of line C, a much steeper line, and you'd end up much lower. You'd have much more static pressure drop, and you'd have much less airflow down at C. Well, my alternative was option B. And so in the 10-inch duct, it matches the slope. There's a steep drop in static pressure where it hits that transition. And then that little mid slope there, you'll notice it's parallel to the red line because it's an 8-inch duct. There's another drop from the other transition, but then the rest of that slope is not as steep. And so you end up at B, which was above where we needed to be. So it just shows that, you have to imagine the molecule going the entire distance of the air. And instead of making it a high resistance from the very beginning to the very end, you make it a low resistance, and then for a short period of time, you make it a high resistance, then go back to the low resistance. So that's what that's about. And that's somebody at the symposium started talking about these lines. Oh no, it was at the house. Is when we were talking about. We were trying to explain to January about how the pressure, and we showed the slopes of these lines. I think that's a very useful tool in some cases. But anyways, that's what that's all about.
So this reminds me of a job, but it wasn't about duct. It was about refrigerant flow. And this was like an existing install, and the line set was too small, and the lady didn't want a line set on the outside of her wall. You weren't going to be able to cut the wall open. It was like a 3/4 inch line set on like a 4-ton or 5-ton unit. And so we discussed with an engineer what we could do. And he said, put an 1.1/8 suction line all the way to the unit, to the wall, and then outside the wall to the unit. He says, increase everything you can and leave what's in the wall. And it worked better, but it kind of makes me think that the same principle's at play.
Right.
Pressure drops only in that short run of the, refrigerant line rather than the whole line.
Yep.
You know what I'm saying?
Yep, same principle, exactly. Yep.
that's why we need these engineer types to explain this stuff.
Yeah.
Us knuckle draggers.
Yeah. But the one topic I wanted to discuss that kind of came up with that too was balancing room loads, mainly talking about return air balancing, right? Being we're talking about duct pinch down, back up, or small or whatever. I know, Russ, this is like a pain point for you, right? Because you got a good story about dedicated returns and balancing rooms.
Yep.
And my question is if someone's gonna design a job, what's the best method if you're gonna balance the rooms?
No doors. Don't allow them to put any doors.
That's a winner right there, man. No
Yeah.
doubt.
Yeah. You're like a hippie commune. Everything's wide open. There's no doors. There's no privacy. You don't need privacy.
Well, like for my area, right, we don't have dedicated returns in every room. But if you go to a homeowner and you say, hey, look, we got to do passive grills, they're going to go, nope, that ain't happening in my house. And they literally will tell you, my neighbors don't have it. My house isn't going to have it because I don't want any problems trying to sell this house. That's the answer you get.
Yeah.
You know?
Interesting. Yeah. Well, I was convinced to do it. And when the builder told me, I was like, that sounds like a really great idea. And I was really, at first, I was really into it. I was excited to design a subdivision. It was a builder had moved out from the East Coast to Las Vegas and wanted to bring his ideas, out to Las Vegas. And they said, I want to return in every room that has a closable door. I want to return in that room. And I thought, wow, that's kind of cool. Let's try that. I was really interested in it. But man, did it turn out, not only was it a nightmare, you've got almost twice as much duct to fit into a house, right? So that's the first problem. You've got twice as much resistance to airflow. You've got twice as much surface area that's going to conduct. So all of those things add up. Those are bad to begin with. But what I was really surprised was how hard it was to balance that house. In Las Vegas was the very first city I ever ran into that required stamped mechanical plans by an engineer for a house. And if it was a subdivision, the sales models had to have an air balance test on them. And you had to write down, and it had to be plus or minus 10% from the design CFMs at each register. So they built these sales models, and we were trying to balance them, and it was a nightmare. It was an absolute nightmare because you'd adjust the damper on the supply, and the return would start sucking more air out, and the rooms next door would start affecting it. And then, heaven forbid, you did a test with the doors open and closed. It just throws too much. I don't know. It just throws too much unknown into the whole process. And then the other thing we discovered is that it stops the airflow through the hallways, right? So now the hallways are no longer being used as, ducts. Eric Kaiser had a great presentation at the symposium about, is your house part of your duct system, right? And it is. Your hallways are return ducts, basically. And now you're not using them anymore. And the way I describe it is, if your thermostat is in the hallway, you want that thermostat to have to have air coming past it that's coming from as many rooms as possible. And when you have put a return in a bedroom, you're taking that bedroom's vote away. There's no air from that bedroom passing the thermostat anymore. It's going straight back to the return. And so it takes away the thermostat's ability to do a better job sensing the air. What you want is as much air from the house to go past that thermostat so that it's sensing the temperature. One of the things I like to do when I go out to a house that's having temperature problems is I'll stand next to the thermostat. I'll kind of stand with my back to the thermostat and figure out where the return is and say, okay, where is the air? What rooms are coming past this thermostat to get up to that return? And, and sometimes that can have a big impact on a thermostat's ability to sense the whole house. And, if there's a whole bunch of air coming out of a bathroom and going past the thermostat, then the only comfortable the only comfortable room in the house is going to be that bathroom. And so there's weird things like that can happen too. And so just putting a return in every bedroom just causes more problems than it solves. So, I was kind of joking about not having doors. if you kind of start there, say no doors, say, okay, well, we have to have doors. So put a door on there. What's the next alternative? And that would be some sort of a louvered vent. And then the next one would be some sort of, jumper ducts or something like that. But, you just got to get that air back to the bedrooms. And I've also found that if you do a good design, those problems are much less noticeable than in a bad design. If you've oversized your equipment and undersized your ducts, then getting that air out of that room is really important. You're going to have all kinds of problems. But if you do a really good design, opening and closing the door to a bedroom, it's still important. It's just not as important, to make sure that you have some sort of bypass across the door or something like that. And so, I always say good airflow, good overall airflow, good design forgives a lot of sins. And I start there.
All right. Well, look, we're closing in on like an hour. I don't want to waste too much of your guys' time, but I do want to give Russ you a shout out for KwikModel. So if anybody's watching, listening, let's jump into that for a minute. So Russ, you have like a blog website, right?
Mm-hmm.
And I love the title, offering good advice, whether you want it or not.
Yep.
If you know Russ, Russ is a funny guy, right? You've got some good articles in there. I've read a bunch of them.
Yeah, thanks.
But let's talk about KwikModel, right? It's a new design software. Russ, if somebody wants to jump into KwikModel and they want to learn it or see it, where do they go?
Well, if you see in the lower left-hand corner there, it says 30-day free trial. That's probably the best way. Just check it out and play around with it. And, I've used the other software, both of them, the two big software out there, since they came out, basically. And I've taught people on them. I've always been frustrated with them. I just got tired of, going through a 3-day class and having contractors walk out at the end of the 3 days going, yeah, you did a great job, Russ, but I don't have time for this. There's just no way I can get this into my business model. It just takes too much time. And that just haunted me for years and years. And finally, I've tried to get people to make new software. And finally, my son Connor graduated from college with a degree in computer science, and I hijacked his career. He wanted to design video games. I hijacked his career. I convinced him to do something more productive and beneficial to society than shoot 'em up games. And he and I have designed this software with the 30 plus years of my experience doing HVAC design and his amazing computer programming skills. I've been thoroughly impressed with his ability to do stuff when I ask him to. And I know some other people have like Jenny has his phone number. Jenny will call him up and say, hey, Connor, can you make the supply ducts be a different color than the return ducts? And he knocks it out in a few minutes. So we've been having a great time. We've been having really, really good response. Now that COVID is over and we can start having trade shows and getting people to sit down and actually play with the software and use it, we've been getting great response.
What shows you headed to, Russ, with KwikModel? Where can people expect to see you?
Yeah. So we're going to be at the HVAC Excellence in Las Vegas. We're looking forward to seeing you guys there. It was funny. My brother-in-law and his wife are retired and live in Las Vegas. And we were there at the AHR Expo. We had dinner with them. I said, hey, I'm going to be back in a couple of months. He goes, oh, where are you going to be? We're going to be at the South Point. He goes, that's my second home. So my brother-in-law practically lives there. So we'll be. Nice. By the way, he's a professional poker player too. So
I thought you were going to say he's a professional gambler.
He is, yeah. He went from horses to poker.
We got to make sure we hang out with that guy.
Yeah,
I thought he was going to say he goes there for the prime rib because they got like the best prime rib in Las Vegas supposedly.
Yeah, so we're looking forward to that. We're doing one just before that. It's KBEC. It's in California Association of Building Energy Consultants. We're actually driving from our house in Sacramento to Temecula to Vegas, and then driving from Vegas back to Sacramento. And we're going to go up the backside of the Sierras and take our fishing poles with us. So that should be a nice trip.
That's cool.
Yeah, sounds really cool.
Yeah.
All right. So if anybody's watching, they want to know what's in store. Me and Ed had this talk, and we wanted to bring a mechanic on here, and we wanted to discuss like people who take like what we've been talking about with Russ and put it into practice. Someone who's like done it. And so I reached out to a friend of mine. We know Joel Becker, and Joel Becker said, Okay, I'm in. So April 7th, 7 p.m. Central Standard Time, Joel Becker's going to join me and Ed, and we're going to talk HVAC system commissioning, which I think is going to be a fun one.
Yes. Looking
So-
forward to that.
Yep. All right. Thanks, Russ. Appreciate it, Ed.
Thanks,
Yeah.
guys.
I'll see you
See
guys in a couple of weeks in person.
Oh, yeah.
Sure I'll see you on the computer like in an hour.
I'll be hanging
I
out.
gotta
with
go. I gotta go
professional
watch
gambling.
my thing from the symposium again. I just got that on a constant loop, and I just keep watching it because it was so good. That, and I watched Jenry stumble through some stuff. I thoroughly enjoy watching him as he starts to grow as a presenter, and I can feel his anticipation to get all his words out, and I see myself a long time ago. It's good stuff.
Yeah.
It is really good.
Hi, guys.